Okay, so this is chapter 8. Now, chapter 8 is a continuation from chapter 7 and the kind of a combination with our periodic trends that we saw in chapter 4, right? So it's kind of us putting some of those pieces together. So once again, we have a review question for this, right? And so which one of these is going to show our valence electron configurations for our sulfur? And so what we're looking at is we're looking for the orbital diagram. So look at sulfur, and you want to look specifically for its valence electrons. So sulfur's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. And so when we look for our valence electrons, we're looking for the ones with just the highest n value. So just these 6 right down there. So when we look at our answer, we want to make sure that we're talking about the valence ones. So we can already take out C because we're not in the 2s. We should have 2 electrons in our 3s. So we can take out D. And then we should have 4 electrons in our 3p. So we know it's going to be A or B. And so looking at these, the only difference is that A has them all unpaired and then only one paired, whereas B has both of them paired up. Now, according to Hund's rule, we have to fill in each orbital before we double them up. And so we should be number A for our answer because we filled in each of those orbitals. We don't have any empty orbitals like we do in B. Now, while we have our electron configurations, there are irregular electron configurations. And the difference between these is that while we know that there's some energy level difference for each of those sublevels, as our energy levels go up, those energy levels become closer and closer together. And so when they start to split with our S, P, D, and F energies, there can start to be overlap. And that overlap can cause irregularities. And because not all of them will have the same amount of interactions in their penetrations and their electron-electron repulsion, then our electron configurations can become more difficult to predict. And so all electron configurations, they have to be found experimentally. We have to go out, we have to measure them, so that way we can see how many electrons come off at each of those given values in order for us to identify the electron configurations. So a lot of our irregular ones are going to be in our transition metals and our rare earth, or the lanthanides and actinides. And so in your book, they give you a table that has all of the electron configurations, and you can see there's all of these ones that are irregular, and you have these blue or red ones, which is a lot to memorize. You can also see them highlighted here, or at least some of them highlighted here. And since these are experimentally found, there's not always a rhyme or reason to why these are the way that they are, in what electron configuration they take on. And so that can be a challenge for us. It can be very difficult for us to go through and come up with rules about why one is irregular and one is not. So for our class, we're going to reduce that down. We're going to take this down and we're only going to memorize these 7. So we're not going to memorize all of them. We're only looking for 7 irregular electron configurations. And it's because these 7 follow a pattern, whereas a lot of our other ones might not. So the 7 that we want to do is chromium, molybdenum, copper, gold, and silver, GD, and CM. And so the idea behind them is that these top ones, these transition metals, they fall into 2 categories. They take half of their, they take one of their electrons from their 4s and they move it into their d orbitals. So they move one electron from the s to the d's because they prefer to have that half-filled shell. There's a benefit for our d electron to have 1 electron in every orbital compared to having, and only 1 in the 4s, compared to having 2 in the 4s and having a completely empty orbital as seen there. And so when we look back at our periodic table, you can see those two right there as following that half-filled shell. Copper, gold, and silver, on the other hand, they follow something similar in that they're trying to take one of those 4s electrons away so that way they can bump up into the completely filled D level. And so that's how those top two get theirs. The rare earth metals, they do a little bit different. For them, instead of the irregularity happening before the half-filled shell, where they're taking from the S, instead what happens is they keep the half-filled F orbitals and they place one into the D orbitals instead. So these are the 7 that we need to memorize for our class for their irregular electron configuration. Today's class, what we're going to focus on is how we develop periodicity. So we knew about periodicity from when we talked about the periodic table the first time. We talked about the trends, size, ionization energy, electron affinity. But now we're going to talk about how things like effective nuclear charge, atomic structure leads to those things. So we already know what the trends are. We've seen them before. Today, what we're going to focus on is why. So it's not going to be enough just to know the trends. Now we have to be able to explain why. So inside the group, the reason why we started to list the groups together is that they have similar electron configurations. It means that their valence electrons are in similar orbitals, so their chemistries behave similarly. Our noble gases have a complete p orbital, which kind of makes them inert because they're not looking for any more valence electrons. Whereas our alkaline earth, they only have 2 electrons in their s, and so they're willing to give away those 2 to engage in their different chemistries. Now, as we're going forward with this, the important part that we're going to talk about in using our explanations is going to be effective nuclear charge. Now, effective nuclear charge, as we discussed on Tuesday, is it's going to be our nuclear charge, which is our number of protons. And we're going to subtract from it the number of core electrons. So these are electrons in energy levels lower than it. Now, how that trends is inside of a period, our Z effective kind of increases to the right. And going down a column, our Z effective actually gets a little bit larger as you guys go down the column, though with our equation, they're going to end up being the same. Now, remember, effective nuclear charge happens because there's screening. Screening is because these inner electrons, their electron-electron repulsion kind of blocks out the positive charge that they see from the protons for the outer electrons back here. So when this electron is looking in, it doesn't see as much of that nucleus as it used to. It only sees it similar to that +1 charge because it's being screened by those core electrons. So effective nuclear charge is how we talk about the impact of those core electrons as they kind of keep those outer core electrons apart. And so the charge of the nucleus is this black line right here. You can see how it trends upwards. As we increase our number of protons, our nuclear charge will always go up. More protons, more charge there. And so there's different ways for us to measure our Z effective. And you can kind of see the simplest one, this 1s. All they've done is they've just subtracted those 2 electrons that you see from your nuclear charge. And it doesn't give us a very good model because it doesn't take into account when we get to the next energy level. And so the way that we're measuring it is this green one here. This is our estimate that we're doing. And you can see that while it does a decent job, it's not necessarily the best out of ours. It does match fairly well in that it predicts this similar shape as we get with the advanced ones. But it doesn't quite mirror them as well as we necessarily would like. We do have quite a big gap there. Let me get a different one. We do get quite a different gap here. We start to see it building again. But these more advanced techniques, these better methods to estimate that Z effective, they're much more involved, harder to do, and they generally involve computer models. Or at the very least, a graphing calculator. And so we're not going to try to match our Z effective or predict our Z effective using those advanced techniques. Instead, we're going to use our more simple and our rough estimate here. And so we're going to use that one. Now, the thing to remember about effective nuclear charge is that it always increases across a period. So within the same energy level, the more protons you have, the higher your Z effective is going to become. What might not be obvious with our method is that it does increase slightly going down a group. And that's because when we have a core electron, it doesn't completely block out one proton. If you imagine yourself, if our nucleus was a stage and you were sitting in the rows of a concert, those people in front of you, they might block out some of that nucleus. They might get in the way of some of your view. But they never do a perfect job of being completely there where you can't see any of the nucleus. And so that's why as we go down a group, while we're estimating it as Z effective is equal to Z minus S, this S is always going to be slightly smaller than the total number of core electrons. And so while we're making that estimate now, that's why we have a tendency to vary too high, is because we're making that estimate like one core electron completely blocks out a proton. And it's not actually true. So as you move farther down, your Z effective actually slightly increases. Now, the effective nuclear charge for your orbitals is also a little bit different. And so electrons in S versus P versus D versus F, they feel different amounts of effective nuclear charge. S feels the most, F feels the least, which is kind of how we get the splitting of our energy levels. But the reason why this happens has to deal with their penetration. And so penetration is basically how far our shape of those electrons, their probabilities, how far they can exist where they overlap with a prior orbital. You can see that the S penetrates a lot more in there compared to that of the P. And so they feel a little bit more attractive force to the nucleus. And so they're not shielded as effectively. You can kind of imagine that they're a little bit taller, right? Penetration is similar to being taller. It's harder for those electrons to shield you out, right? So you can kind of penetrate in there. Now, we already talked about our valence electrons and the core electrons, but we do want to clarify this for something like transition metals, because it can be a little bit confusing. So what I would like you to do is I want you to go ahead and write out your electron configuration for iron. All right, what is the electron configuration for iron? And once you have that, then I want you to tell me how many valence electrons there are. And then if I was going to ionize it, turn it into Fe2+, what would that electron configuration be? So pause the video, go ahead and try. And so your iron should have looked like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, right? That should be our electron configuration. But we only have 2 valence electrons. And the reason for that is when we're talking about valence electrons, we're only talking about the ones that have the highest values of n. So that's only those 4 s ones. So even though the 3d6 comes afterwards, they aren't going to be our highest one. It's kind of like when we add in the d orbitals, we kind of bury them a little bit beneath the surface. The surface is going to be our 4s2. So when we first form cations, we actually form them by losing those valence electrons. So the Fe2 plus cation that you wrote out, its electron configuration shouldn't be 3d4. It should actually be 4 or 3p6, 3d6. So what we've lost is we lost our 4s electrons because that's where our valence electrons are going to come from. So they're the first ones that we remove. That doesn't mean that it's limited to that. We can actually remove one more electron from there. This is where we become Fe3 plus, and you can see how we become a half-filled D shell. And so that's why iron can have multiple valence states, is because it can lose some from its valence electrons. It can also lose another one from the 3D, so that way it can become this more stable half-filled D shell. It can even lose more than that as well, depending on what's going on. So our transition metals, they get more complicated because they can form many ions. They can form many ions because they have different energies. They have valence energies, but they could also lose even other electrons past that as they're looking to get to its stability. So the first trend that we're going to try to explain with our quantum mechanicals, our quantum mechanics, is going to be our atomic radius. And so our radius, I have a tendency to use size, but we're really talking about radius, is related to the distance that the valence electrons are from the nucleus. Our valence electrons are in the farthest orbital because they are in the highest n value. So the larger the orbital an electron is in, the farther it is from the nucleus, and the less attraction it's going to feel. So if you imagined our nucleus being that center, the closest value in, that closest orbital is n equals 1. As we increase, it becomes n equals 2, n equals 3. And so each energy level, as it increases in its energy, it's a little bit farther away from the nucleus, so it has more energy, and so its distance is a little bit farther as well. So when we go down a period, the reason why our atomic radius increases isn't anything to do with Z effective. It actually only increases because this energy level has increased. We had to go farther out in order to grow our energy level so we could have that higher energy and we can fit more electrons. So quantum mechanics predicts that atoms should get larger down a column because every time we go down the column, we have to increase that principal energy level. We have to increase our n value. For a period, we know that a period atomic radius decreases across a period. And the reason why it decreases across a period has to deal with our Z effective. So if we were to compare something like lithium, carbon, and fluorine, lithium has a lower Z effective than carbon, which has a lower Z effective than fluorine. So the reason for this is that both of them, or sorry, all three of them have the same number of core electrons. They all only have 2 core electrons. But fluorine has 9 protons. Carbon has 6. Lithium has 3. So when we subtract those 2 electrons, those 2 core electrons, our Z effective becomes a +7, a +4, and a +1. Now, the closer that you are, the stronger the attraction is. So the more Z effective you have, then the smaller your radius should be, because you're going to pull those electrons in closer. Right? So stronger attraction leads to a smaller radius. So across a period is Z effective. Going down the column, that's going to be because of their energy levels. Now, when we get to our d orbitals, so our transition metals, what's happening there is that our d block, they all kind of have the same size roughly. So all of our transition metals roughly have the same size. And that's because that D1 is no longer your valence shell. The valence shell is really the ones in the S, not the ones in the D. So us adding in more electrons into the d orbital doesn't really change our shape so much. And so the effective nuclear charge of those S orbitals stays about the same all the way across the D block, because we add in one proton, but we also add in one electron into our core energy level. So this is a practice, right? So we know that Z effective generally increases when you move down the column of the periodic table, because those core electrons don't necessarily shield one-to-one with the proton. We saw that the size of an orbital actually increases going down, or increases with our quantum number, so as our energy level increases. So do these trends kind of work together, or are they kind of in contrast with each other? Because one's saying that as we go down the column, our Z effective is getting better. The other is saying that as we go down the column, our N value is going up. And so do those help, or do those not help? And if they don't help, which one do you think is going to be larger? So because we know that our trend does, our radius increases as we go down, and these two things should be working against each other. Higher ZF should lead to a smaller radius. Then the trends are working against each other. So we know that they're not working to get together, but they are working against each other. And so if our radius is increasing going down, then it's not going to be the ZF, which is going to be more dominant. What's going to be more dominant is actually the orbital size. So the N value, it's the stronger trend when we talk about atomic radius and their comparisons. So if you're in the lower period, you're going to be larger than something above it. And the reason for that is that each time we go into new energy level, we have to do a big jump in our radius, because we have to be in a farther out energy level. Our ZF just kind of squeezes each of those rings as we add in more protons, but it doesn't change how far apart they need to be. One thing that we were going to talk about is magnetism. And so magnetism has to deal with our orbital diagrams. So electron configurations are a great way for us to explain whether something's magnetic or not. Because if you're going to be magnetic, it means that you have unpaired electrons. So if we look at iron, iron is a magnetic element. It's got 2 electrons in its S, and then it's got 6 electrons here. So you can see that it has 4 unpaired electrons. That's called being paramagnetic. And that means it's going to be interactive with the magnetic field. So if we put a piece of iron next to a magnet, we should be able to pick it up. And that's because it has those unpaired electrons involved. On the other side, if all of those electrons were paired up, so something like zinc, zinc has 10 electrons in its d orbital. It's got 2 electrons in its 4s, and so all of those are paired. And so zinc doesn't respond with a magnetic field. If we put a magnet next to it, it doesn't get attached to it. And that's because it's what we call diamagnetic. All of its electrons are paired, so it's not going to interact with the magnetic field. So paramagnetism means that you are attracted, diamagnetic means that you are slightly repelled. But really what we're talking about is unpaired electrons versus paired. The more unpaired electrons you are, then the more magnetic you'll be. And so nowadays you might go out and buy those really strong, and they're called rare earth magnets. And that's because they use elements down in the rare earths where they can have a lot of unpaired electrons, because the F group has 7 orbitals. So they can get all the way up to 7 unpaired electrons in the F group alone. Whereas our transition metals, they can only ever get up to 5 because they only have 5 orbitals for the D. And so that's our magnetism. Now, atomic radius has another side of it, and it's called the ionic radius. So for an ionic radius, we're talking about ions. And so for our ions, they kind of follow the same rule. Ions in the same group that have the same charge, and so they increase down the column. So things like lithium plus versus potassium plus versus sodium plus. Lithium will be smaller than sodium, which will be smaller than potassium. Cations are smaller than the neutral atom that they're coming from. Oh, sorry. Cations are smaller than the neutral atom that they're coming from, and anions are larger, like this picture here. Pretty much when lithium loses that 1 electron, it shrinks drastically in its size because now it's gotten rid of that extra electron. And so cations, for the same number of protons, they have less electrons. So there's less electron-electron repulsion, allowing them to be smaller in its size. On the other one, anions, they have the same number of protons as before, as their neutral one, but they have more electrons, so there's more electron-electron repulsion, and so they are larger in size. And so that's the difference for our cations versus our anions. Cations are always smaller than the atom that they're coming from. Anions are going to be larger. If we look at those families, like what we talked about earlier, you can kind of see how their radius is increasing, going down, for all of them being the same size. The same thing is true for our anions. So iodine, -1, so iodide, is larger in its size than something like bromide, chloride, or fluoride. Now, the other part about them is that cations are almost always smaller than anions. It's not until we get really far apart, it's not until we're comparing something like rubidium and cesium versus our fluorine and our oxygen, do our cations finally have a size to compete with that of our anions. And so becoming an anion really increases your size. Becoming a cation really decreases your size. You can kind of see that here, right? Fluorine is 119 nanometers across. That's comparable to something like sodium plus, right along with potassium. Chloride, similar to potassium or rubidium in its size. So them being negative has really increased the size in comparison to them. Now, the other thing we want to talk about is something that's isoelectronic. So isoelectronic means that they have the same electron configuration. So if we were to talk about neon, neon has the same electron configuration as fluorine minus. It also has the same electron configuration as sodium plus. All of them are 1s2, 2s2, 2p6. So when we're trying to compare our atomic radius, if they are an isoelectronic species, we can still compare them. That means that if we wanted to compare these three, we should be able to. So neon could be our starting point. It's right there in the middle. And then we want to compare them next to each other. Fluorine has to be bigger than neon because it's an anion of it. And we know sodium has to be smaller than neon. So it's got to be the next one down. When we add in something like magnesium 2+, magnesium's 2+ is even going to be smaller than that because it still has that same electron configuration, but now it's got another proton compared to that of sodium. So the thing about isoelectronic is that they all have the same number of protons, same number of electrons, which is why they have the same electron configuration, but they have different number of protons. The more protons you have, the stronger the attraction. The stronger your attraction, then the stronger your attraction, then the smaller your radius. And so that's kind of how our sizes of our atoms take place. Right? So you can kind of imagine that when atoms form cations, they're losing those valence electrons. When we remove those valence ones, then the farthest electrons become the p and the d from that next energy level down below. And so that means that they've got to be smaller. They don't have to go quite as far out. New valence electrons experience a larger effective nuclear charge than the old valence electrons, and so that shrinks the ion even more. So not only do we no longer have that extra energy level, but we also feel more Z effective. So we got to decrease that even more. When we go down a group, well, we're going to be larger cation to cation compared to the other one because we're still increasing our group size. And then when we go right across the group, the effective nuclear charge for those isoelectronic cations continues to increase because we have even more protons. And so that means that our cations continue to get smaller. And so those are the explanations for our cations from our quantum mechanics. For our anions, we're now adding in electrons to that valence cell. So these new valence electrons experience a smaller Z effective than the old ones because there's even more of those electrons. And so our anion has to get bigger. When we go down, we still increase our N value. And so going down the column, we get even larger. And as we move farther and farther across with more and more electrons, then we still feel less and less effective nuclear charge. And so we cause our anion to get larger. Right? So that means that when we compare O2 minus versus F minus. O2 minus is larger than F minus. Right? So our anions are larger with more charge. Our cations are smaller with more charge. So try that out. Which direction should it move? Is it getting smaller, same, larger? So if they have the same charge and we're going down the period, then they're going to get larger. Very good. The next one that we're going to talk about is ionization energy. So ionization energy is defined as the minimum energy needed to remove an electron. Now, each ionization energy only corresponds to removing one electron. So IE1 removes the first electron. IE2 removes another electron, but it doesn't remove it from the neutral atom. It removes it from the +1 ion. So each time you go through it, you have to do each of those ionization energies separately. Right? First one and then the other. Now, normally we always remove them when they're at a gas state. And this process is what we call endothermic. So it always takes in energy for us to remove them. So the general trend is that as we go down the group, our ionization energy becomes easier. So it's less energy required. And that's because those valence electrons are farther from the nucleus, so they're not held as tightly. So it makes it easier for us to remove them. They also generally increase across a period. And so that was what we used to know. We used to know that as we went across a period, our ionization energy would go up because their effective nuclear charge has increased. But now our model has gotten a little bit more complicated. You can see something like this. Our ionization energy, well, as you can see on the periodic table, it decreases going down, and it generally increases to the right, but there's some variations in there, some disconnects. So our overall trend stays the same, but now we should understand it a little bit better, and we should understand where these disconnects happen. So one of our first exceptions in ionization energy trends is that when we say it increases from left to right, what's going on is between beryllium and boron, we see our first break. And that's because when we ionize boron, we're removing this 2p electron versus when we ionize beryllium, we're removing this paired one. And so that paired one, that 2s, takes more energy to remove it because this 2p starts off slightly higher in energy. So the higher you start off in energy, the easier you are to ionize, because imagine that your electrons are kind of like in a hole. And so the nucleus is down here at the bottom of that hole. And so the lower your energy is, the farther or the more energy we have to put in to get it out. So between our 2s and our 2p, the 2p is just that little bit higher than our 2s, makes it that little bit easier for us to remove. Now, once we get into our second one, so once we move on to carbon, that benefit gets offset because every time we add in a proton, we kind of drag this hole deeper down, right? Their effective nuclear charge is a little bit higher. The second break that we see happens between 5a and 6a. So this is between nitrogen and oxygen. And so nitrogen, to remove that one, is a higher energy. Then our first paired one for our oxygen. Because this paired one, those paired electrons have slightly more energy than unpaired. And so it's a little bit easier to remove them. And so that's why our picture is not as clean as what we used to see. This one is that break between our s orbitals to p. This one is a break between our p to our our paired electrons, so unpaired. And now I want you to take a moment and think about, well, what is this one? What is that really large transition? And if you can figure it out, then that's great. This really big change happens between our energy level. So when our energy level increases, then we see a big dip in ionization energy because it's significantly easier to remove ones in higher energy levels compared to the other one. Very good. So looking at our nitrogen and our oxygen, I want you to predict which one is going to have a higher ionization energy. And why? Now that you have your answer, see which one of those will line up with your thoughts. And what we should be looking for is C, that the 2p electron from oxygen is in a fully occupied orbital. That means it's paired. And so it has increased electron-electron repulsion compared to that of our nitrogen atom, which makes it easier to remove. So our oxygen has a lower ionization energy than nitrogen. So it's not that it has a lower Z effective, it actually has a higher Z effective, but it's because of that extra electron-electron repulsion. So when you talk about ionization energies, you really want to be focusing on the strength of that attraction. And then you also want to be focusing on those orbital values. Right? So the strength of the attraction is related to the most probable distance, right, and the effective nuclear charge. So the larger the orbital, the farther its probable distance, and the less attraction it feels, so the easier to ionize it becomes. So that's how we predict top and bottom for the ionization energy trend. Across it, we predict that there's an increase in effective nuclear charge, and so it should get larger across a period. Now, the other side of this that we're not taking into account is the electron-electron repulsion. And that's where we get the paired versus unpaired. We also have sub-level splitting, which is where we get our S versus P versus D energies. Very good. Now, there's another thing that we can do with ionization energies, and it's called successive ionizations. It's when we take one electron away from the second. Or sorry, when we take a second electron away after we've taken the first. So I want you to think about, how do you think they compare? And if you answered that they get larger, you were right. The second ionization energy, the second electron, is always harder to take away than the first. Because after we remove that first one, we've removed some of that electron-electron repulsion. And so there's always going to be a jump in its energy. It's always going to be harder to remove it the second time. But sometimes what happens is when we remove another electron is that there's a huge change in that energy. And that's because we might be removing that next electron from a full subshell or a half-filled subshell. and that makes it significantly harder. And so we see that, we track that for successive ionization energies, and it helps us identify elements. So when we first remove it, there's always some shrinkage because we have more protons than electrons. And so those allo electrons are a little bit closer and a little bit harder to remove, so that always increases a little bit. But when we remove a core electron, there's a big jump. So for something like sodium, you can see the big jump occur between IE1 IE2. It's almost 10 times bigger for its change. So it got a lot bigger. But for magnesium, that big jump didn't happen between IE1 and IE2. It happened between IE2 to IE3. So where that jump occurs tells you how many valence electrons it had. And then that next one where the jump happened, that's when we got into a core electron. So sodium, we could remove one electron from it, and then we felt the jump when we removed the second. So that means that sodium should make an Na plus. It can only remove one valence. Magnesium, we removed two of them before we felt the jump, and so we can make a magnesium 2+. So if we keep ionizing an element, an unknown element, we can eventually find out what group it should fall in based on its jump, when that jump is going to happen. So for chlorine, you can see that we can keep increasing it. It goes up, goes up, goes up, goes up. And then over here, we would see that jump. I guess chlorine was a bad example because they actually didn't give us that value. So let's do that again with sulfur. Sulfur, you can see that there's a constant increase here. Each time is going up about 1,000, 3,000, 1,500, and then it goes up a whopping 19,000. And so this is where the big jump happens. So when you're trying to compare things, once you have all of that, you want to be looking for the big jump, and that's telling you when you start to remove a core electron. Ionization energies are very useful for us to talk about reactivities, because the more reactive you are, then generally the easier you are to ionize. So cesium tends to be the most reactive of the stable alkalis. So we're not talking about francium because it's radioactive. And so when we think about why cesium ends up being so reactive, it's not because it's dense or conductive or it's got a lot of electrons. Really what it is that it's easy to make into an ion. And the easier you are to turn into an ion, then the more chemistry you can get involved in easier, because the energy required to start off that process is a lot less. So things like copper, silver, and gold, it's not that they're not abundant, or sorry, it's not that other metals aren't as abundant as them, which is why we've known about them for so long. But what property is it about copper, silver, and gold, which is why we were able to isolate them earlier, whereas other metals we didn't isolate until much later. And it's that copper and silver and gold are less reactive. So they were easy to isolate because they never broke down to begin with. Whereas things like lithium, sodium, potassium, calcium, beryllium, they were much harder for us to identify because they engaged in a lot more chemistry. And so it took more advanced stuff for us to be able to separate them out and purify them as metals. Now, the opposite of ionization energy is our electron affinity. So electron affinity, instead of us talking about removing an electron, it's the energy released when we gain an electron. So this is the process for electron affinity. So it's defined as being exothermic. Even though sometimes you can actually require energy to force an electron to be gained, we normally define it as being exothermic because we normally use this to talk about things that are going to form anions. So ionization energy fits a lot with our metals when we form cations. Electron affinities fits a lot with our nonmetals when we form anions. So What we're looking for with our electron affinities is that their general trend matches that ionization energies in a lot of ways. The only difference is that those jumps, it's still between 5A and 6A, but that's because 5A doesn't want to gain that electron anymore. 6A doesn't want to, 6A wants to continue to gain that electron, right? So when we see those disconnects, we see them happening in a similar way. We also see them happening in similar processes, electron affinity going down as we go down the column, increasing to the right. The other difference is that our noble gases, they're not involved in electron affinities. Our noble gases don't want to gain any electrons. This is different than that of our ionization energies, because ionization energies, we can still remove them. They're very high, whereas electron affinities, they're kind of not even involved. Okay. So knowing what we know about our disconnects, I want you to look between group 4A and 5A. So group 4A has more negative electron affinities than group 5A, right? Or group 14 and group 15. So this is carbon versus nitrogen. So it's not that nitrogen doesn't want to eventually gain electrons. It's just that on that first one, it can be hard to do. And that's because group 14, when we pick up an electron, we become a half-filled P3 configuration. So we go from having 1 in each to having 3. Whereas our group 15 goes from having 3 to having 4, which is not as preferred energetically speaking. And so that's the difference in the electron affinities. So same thing as what we saw with the ionization energies, slightly different reason. The last part of what we're going to explain is going to be our properties of metals. So which ones are metallic versus which ones aren't. Right? So just remember that our metals are pretty much those ones that become cations, lose electrons in reactions, so they oxidize. Right? Our nonmetals, they're typically brittle in their solid state. They don't really conduct electricity. And when they do get involved in redox reactions, they're going to be the ones that reduce. So they form anions or polyatomics. So our trend typically follows the same thing as what we normally would think. Metallic character increases down, decreases, or increases to the left. And so the idea behind it is that metals generally have smaller first ionization energies. Nonmetals have larger electron affinities. So our metallic character, we think it should go down because the valence electrons are not held as strongly, making it easier to ionize. So it's easier to become a cation. And it decreases across the right because those valence electrons, they feel a higher ZF. They're held more strongly, and the electron affinity increases. So both of those things kind of go hand in hand. Now, let's try to use and apply some of our knowledge now to make some explanations. And so this is the hard part with chapter 8. Chapter 8 is not really about math. Chapter 8 is about us explaining trends. So not just using the trends, but being able to explain why they are the way that they are. So start off with just this part. Which one do you expect to be more or less reactive with water? Potassium metal or rubidium? And so rubidium, we should expect to be more reactive than that. And now I want you to come up with an explanation. Why? So you could say rubidium metal has a lower ionization energy because its valence electrons are in a higher energy level than potassium metal, making rubidium an easier to ionize metal and a more reactive metal. So we explain what trend we're looking at, right? We're talking about ionization energy. We also explain why the ionization energy is true for that, right? We explained that rubidium metal, the valence electrons are in a higher energy level. And then we connect that back to the reactivity part. So we draw a line connecting rubidium to potassium to reactivity, and we're using quantum mechanics to do that. So we don't want to just say that because it's lower in the period. That just lets me know that you know what the trend is. It doesn't mean that you understand why it makes the trend. So whenever it's talking about using quantum mechanics, we should be thinking about things like Z effective, shielding, energy levels, orbitals, a lot of things like that. The mechanism for why, not just the trend. This one's asking you to use trends in ionization energy and electron affinity to explain why calcium fluoride has a formula of CaF2 and not Ca2F or CaF. So you could say calcium has a jump in its ionization energy from IE2 to IE3 as it has 2 valence electrons. So the third electron removed will be a core. This means it prefers to make a 2+ cation. Fluorine has an electron affinity increase, or has an electron affinity that prefers 1 electron. Its ion as the second electron. Will be added to an electron configuration that of neon, which is not preferred. So calcium fluoride should be CaF2 to match their ions. That's how you can go through that. So I want you to try your explanation for this one. Now, before you start, right, or if you've already started, that's fine. But if you already started, then I want you to check on whether you have these parts. When you read through a question, it does give you a lot of hints about what we're looking for in order to get all those points. And so it says bromine is highly reactive liquid while krypton is an inert gas, and explain the difference based on their electron configuration. So I can tell you that if you don't reference your electron configuration at all, or if you don't write out an electron configuration, you're not going to get all of the points for this problem, because it's telling you in the problem that we want an electron configuration. The second part is it's then having you compare highly reactive versus inert. You can also talk about liquid versus gas, but that's not something that we have to talk about. But we do want to make sure that we're addressing highly reactive versus inert. So you could say bromine has an electron configuration of AR 4s2 3d10 4p5, which needs one more electron to fill its 4p sublevel or subshell, while krypton has an electron configuration of AR 4s2 3d10 4p6, which is an already filled 4p subshell. Therefore, bromine will be reactive as it tries to fill its subshell, and Kr will be inert as it has all of its electrons that it needs. Okay. Now let's try another one. Vanadium and its 3+ ion are paramagnetic. Use electron configurations to explain this statement. So if you never reference an electron configuration, you're not going to get all of the points, right? And so normally with my questions, I try to help you out. I try to guide you about what I'm looking for that explanation. So you want to make sure that you're reading the questions carefully so you understand what you need to be responding with. So vanadium electron configuration is AR 4s2 3d3, which has 3 unpaired electrons, and its 3+ ion is AR 4s2 3d2. Oh, sorry, not 4s. We've lost the 4s. Which has 2 unpaired electrons as well, since it lost the 2 valence electrons first. You could also have drawn orbital diagrams to kind of help illustrate that. So we have vanadium, and then we have vanadium 3+. If that also helps explain. But you don't want to just write electron configurations, and you don't want to just write orbital diagrams. There still should be some words that correspond with them, so that way we can explain that. For this one, it's having us compare them using our understanding about our charges. And so we can do that by looking at our Z effectives for each of them. So I'm gonna give you a moment to do that first, and then we'll go through it. So Z effective is gonna be our Z minus our S. And so how that works out for us is that oxygen becomes something like 8 protons minus 2, so this is plus 6. Lithium is plus 1. Boron is going to be 5 minus 2, so plus 3. Helium is 2 minus 0, so plus 2. Potassium is plus 1. Cesium is plus 1. Nitrogen is plus 5. So we want to go ahead and we can arrange these by increasing Z effective. So nitrogen is less than that of oxygen, but more than that of boron, more than that of helium. And then we have CS, K, and Li. And so CS should be a little bit more than K. It should be a little bit more than Li. And so we have ours kind of arranged. We could also think of it as being, well, our lithium, potassium, and cesium are all plus 1. Helium is all plus 2. Boron's plus 3. Nitrogen's plus 5. Oxygen's plus 6. And then inside of that column between lithium, potassium, and cesium, we should have cesium being a little bit higher than potassium, being a little bit higher than lithium. And so it asks us to explain the relationship between effective nuclear charge and atomic radius. And so there's two of them that we can talk about, right? We don't necessarily have to focus on this because their explanation for the radius is not tied in with Z effective. And helium, we don't necessarily have to talk about its size because it's in a different group. But we could just focus on the ones that are in the same period. So lithium, boron, nitrogen, and oxygen. So make some space so we can write our explanation. So within a period, the effective nuclear charge increases with a decrease in atomic radius. So all of the valence electrons are in the same orbital. So effective nuclear charge is the determining trend for radius. And that's because when we go for the groups, right, when we compare our groups going down a column, then our Z effective is not the determining trend for radius. Instead, it's our energy level which becomes the determining trend. Now we're looking at bismuth, right? Bismuth is Bi, and so it's asking us about our valence electrons, and then it asks us to do two things. What is its electron configuration and the orbital diagram? So we need to make sure we do both of those. So bismuth's electron configuration, right? In this one we could do either shorthand or longhand. And so shorthand is going to be xenon, and then we have 6s2, 4f14, 5d10, 6p123, And our orbital diagram for our valence electron should only be our 6s and 6p. Since those are the only ones that are valence electrons. We don't necessarily want to include our 4f or our 5d because those are not considered valence electrons. How many valence electrons does the elemental copper have? Oh, I forgot to include this. So we also should say bismuth has 5 valence electrons. So how many valence electrons does the elemental copper have? Write this electron configuration and draw the orbital diagram of all of the electrons in the orbitals with a higher energy than 2p. Is copper paramagnetic or diamagnetic? So we got a couple of things going on there. All right. So how many valence electrons does copper have? So copper's electron configuration is argon. And then we would say it's 4s2, 3d9, except at the beginning of class we talked about copper. And copper is one of those special cases. Copper is an irregular configuration. So it's got an irregular configuration, so we have to make sure that we include the 4s1, the 3d10. It then asks us to draw the orbital diagram of all of the electrons in orbitals with a higher energy than 2p. So 2p is going to be neon, so we should have a 3s, a 3p, sorry, our 4s, and our 3d. Okay, and so now we need to put them in. So we should have 2 electrons in the 3s, 6 into the 3p, 2 more into the 4s, and then we should have, oh, not 2 more, 1 more into the 4s, and then we should have 10 . And so copper has only 1 valence electron. And then it asks us, is copper paramagnetic or diamagnetic? And so remember, para means unpaired. Dia means paired electrons. So we are paramagnetic because it has 1 unpaired electron. Now you can do something similar for tungsten. You can work through that as well. And so just think about what tungsten is, find it on your periodic table, and work your way through that one. So tungsten is similar to our xenon, but 6s2, 4f14, 5d1234. And so as we go through this, then we should have xenon. Oh, so we already have that. So we need to do our orbital diagram. So we need to start with anything higher than 5p. So that becomes 6s. (4f), 5d. So we should have 1, 2, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then our 5D is 1, 2, 3, 4. Okay, and so for our last question, what we have here is explain which of the following elements would have the largest third ionization energy and why. So when we look at these, the third ionization energy, we have bromine, and it's going to be losing its third electron from the 1, 2, 3, 4p, the 4p energy orbital. Fluorine will be losing its third one from the 2p. Oxygen from the 2p as well. Yeah. So when we think about it, between fluorine and bromine, right, fluorine should have a higher ionization energy than bromine because it's losing it from a much lower energy state. Right? So its energy level is 2 instead of 4. So that means that it should have a higher ionization energy, right? Harder to remove those electrons. And then when we compare oxygen against fluorine, they're both losing them from the same energy level, the same energy orbital. And so then we want to be thinking about their Z effective. And so fluorine has a much higher ionization energy than oxygen because it has a higher Z effective than our oxygen. So if we wanted to go through and explain this, we could say fluorine has the highest third ionization energy of the three because fluorine is removing its third electron from 2p orbital, which is a lower energy level compared to bromine, 4p, and fluorine has a higher Z effective than oxygen, so it will have ionization energy than oxygen's 2p electron. There you go. All right, enjoy you guys' spring break.